Hello, my name is Edward Ding, and I am the current president of AVBotz.
Hi, I'm Craig, and I'm this year's software VP. Hello, I'm Justin. I'm this year's electrical VP.
Hi, I'm Andrew, and I worked on the sub's vision system.
Hi, I'm Ryan. I'm working on the hydrophones.
Hi, I'm Arav, and I'm working on the cascaded PID controller.
Hi, I'm Jason, and I'm working on path marker detection.
Hi, I'm Ethan, and I worked on DVL and IMU configuration.
Hi, I'm Richard, and I'm working on DVL communications.
Hi, my name's Dylan Klong. I'm on mech, and I worked on the external components and the conduit panel.
This year, we plan to attempt the gate with style points, bins, buoys, and the octagon.
So for our approach for each task, they all rely on the same fundamental vision subsystem. So first, an ML model in the image detects the object, calculates the angle to the object, and calculates the distance to the object. So with this information, we can feed this into our microcontroller, which pushes our sub to our target destination. And then we repeat all this process in one loop so that we continuously update our trajectory. So for gate, buoy, and octagon, we use this approach. And for bin, we use the same approach, but for the down camera. And then finally, for the path marker, we use an OpenCV-based detection system.
For the past 2 years, we've used a gazebo-based simulator to test our sub's mission code. Our simulator has allowed for significantly faster testing and debugging, saving us the hassle of in-person pool tests. This year, we updated all of the props in our simulator to match with the 2022 RoboSub specifications, and we've used data from our simulator to test and train ML models for our sub's vision system.
Previously, our team utilized the efficient D0 model for object detection for its ease of training and significant detection speeds compared to other models at the time. However, due to the quick changing nature of the field of AI and computer vision, we quickly began searching for an improved model to replace efficient with. After extensive comparison tests with other contemporary vision models, our team chose to implement a new vision system based on the YOLO v5 algorithm. Our main incentives for switching to this new architecture was primarily the significant detection and inference speed boost YOLO v5 offers, being capable of up to 87 FPS, a speed boost of almost 3 times. The lightweight nature of this model also allows for ease of simulation of the vision system, even for inexpensive laptops, and removes the requirement of a heavy, expensive, and power-hungry GPU on board the AUV. Its high update rate also enables us to more quickly and accurately track objects in our camera feeds, improving the accuracy of our angle calculations and control code.
On top of the new updates to the vision system itself, we also implemented CVAT, an automated computer vision annotation tool that allows us to streamline the once tedious and labor-intensive process for labeling the massive image datasets taken from the sim. Now, using its robust interpolation feature, CVAT dynamically overlays labels between manually placed checkpoints that allows us to cut down on the time it takes for us to label and train models without sacrificing accuracy. Now, with this new gain in efficiency and time, it also allows us to redirect our efforts onto other vision pursuits, such as perfecting mission code or ensuring that all competition tasks run smoothly.
For our hydrophones, we needed an algorithm that would allow us to direct our submarine towards our objective pinger to use our vision control algorithm at a greater accuracy. To do this, we implemented a fast-forward transform algorithm that would allow us to convert sound waves underwater into data that we can easily read, filtering out the noisy data and determine if one of these signals received by our hydrophones contains the frequency of our target pinger. We have not yet reinforced this, as we have other things to improve on.
We are currently attempting to switch our positional PID controller for a cascaded PID controller by implementing a primary velocity controller. Our positional PID controller takes the positional arrow, or the difference between our target location and our current location, and then it outputs a velocity set point based on how aggressively we want to reach that location. Our primary velocity controller then takes that velocity set point, subtracts our current velocity from it, and then multiplies that by our motor's orientation to finally reach our location. This cascaded PID controller is an improvement over our positional PID controller, as it stabilizes the sub, it controls velocity limits, and it allows our positional controller to not have to handle all the noise from our sensors, while also controlling the velocity and the position of the sub.
From testing, we realized that the path marker actually had a different exterior color than that of the other objects within the image, which is why we decided to implement HSV filtering, which quickly became the most integral part of our path marker detection system. With HSV filtering, we were able to detect the path marker using 3 color channels: the hue, the saturation, and the value, also known as the brightness, and this is similar to that of the RGB color space. As a result of this, we were able to hone in on the path marker and detect the contours with the lowest hue.
After thorough performance testing last year, we found out we no longer needed an NVIDIA GeForce GTX 1080 Ti to run our inference models. YOLO V5 is much more efficient compared to efficient DET, and we found out that an RTX 3050 is more than enough to run our models. This allows us to increase our runtimes in our pool and the competition. In addition, it allows us to manage our temperatures inside the MEB more easily.
Marlin's old Explorer OEM DVL ran on suboptimal wiring and was prone to breaking down. With the DVL being necessary for the calculation of orientation and relative position of the AUV, our navigation electronics were due for an upgrade. Electrical and software decided on buying the Cerulean DVL75 with an upgraded IMU. With internal magnetometers and accelerometers, an IMU is prone to disturbances from external magnetic influences, and that is where the main sources of error come from. The DVL75 minimizes these errors by separating the IMU sensor head from the electronic stack. The DVL75 also has an extended Kalman filter, which allows for compensation of drifts and offset from external magnetic influences, making it the perfect option for testing in new and unknown environments.
In order for the software stack to communicate with the old Explorer OEM DVL, it required the RS-232 transceivers. Wiring up these transceivers was complicated and made communications prone to failure. On the other hand, the Cerulean DVL75 uses UART to communicate, which requires only 2 wires for communication and can connect directly to the Arduino Mega 2560. This significantly simplified our wire management and made communication with the Cerulean DVL75 significantly more consistent.
NEMO has been designed with multiple modular panels around the frame that can be easily reprinted and manipulated to suit any of our needs. For example, on the front we have the front camera currently sitting on the modular panel. However, if you really need, we can reprint another modular panel that can be used for something else.
Additionally, the batteries are placed externally on the sides. This means we don't have to open the main electronics bay to access them, which means that during water testing, we can improve our efficiency by reducing the time needed to take the batteries out.
Water testing took up a big portion of our time. We wanted to make sure that NEMO was watertight before connecting the electronic systems. With the placement of Presta valves on the electronics bay, we were able to submerge NEMO near the surface of the water and pump air in, watching for any bubbles. Once we were sure that NEMO was watertight at that level, we attached 2 45-pound weights to each side and submerged it for deeper and longer, using carefully placed GoPro cameras to watch for any leaks.
We're excited for competition this year. Good luck to all the teams, and see you guys at competition.